Welcome, and thank you for joining us in this fourth podcast with Dr. Anis Raman, President, CTO, and inventor of T-Ray Technologies for Applied Research in Photonics, Inc., ARP. My name is John Mahoney, President of C4 Technology. We engage in technical sales and innovation discovery solutions for semiconductor and broader industry applications. Today we are discussing part 2 of gallium nitride, and as it is related to semiconductor processing and GaN's extensive application to power and optoelectronic devices. In part 1 of our GaN podcast, we discussed teraspectra cameraless 3D imaging. Today, we will dive into teraspectra, time domain spectroscopy, and its applications with GaN. As a brief overview, teraspectra is a line of scientific discovery tools employing an industry-only, tunable, ultra-wide, broadband terahertz source ranging from 100 gigahertz or 0.1 terahertz through 30 terahertz. This enables cameraless T-ray to 3D image and analyze beyond other known techniques, including AFM, SEM, TEM, X-ray, E-beam, infrared, and other optical techniques. Dr. Raman, welcome and thank you for being with us today.
Thank you, John. Thanks for your tireless efforts.
You're welcome. Dr. Raman, could you please provide a brief overview of time domain spectroscopy?
Absolutely. Well, thank you again for arranging the podcast series. As you have already introduced, that we talked about the GaN in the last podcast, that is gallium nitride, and the slide that here it is showing, it shows that when a GaN film was subjected to electric stress, obviously high field stress, the lattice structure goes under change or damaged. So obviously non-destructively, there is no technology or technique that can be deployed to see what the damage, where the damage, and how much it is, except our T-ray. And this slide shows from the left to right that we have a gallium nitride film grown on silicon substrate or silicon wafer substrate. And then there is a 3 volume. On the second left image is an optical microscope showing certain things on the surface, black spots on the GaN surface. And then the middle one is the volume image generated by T-ray that's showing the lattice scale. This is 5 micron by 5 micron by some probably 3 or 4 micron depth. And that is showing that certain areas, structures have changed. And the rightmost one is on the top surface. That's showing that there are areas where crystalline area remains at the bottom, but from the midpoint on, there is damaged lattice area.
All right. And, of course, today is all about mostly talking about time domain spectroscopy. But I wanted to ask you, you mentioned that other techniques, including scanning electron microscope and TEM, for instance, aside from the obvious requirement of preparation required for those techniques, why and how does teraspectra's T-ray show more than those 2 techniques that are very common and popular?
Right. Both SEM and TEM can see and image the lattice structure. However, for SEM, it's only the surface. we are imaging the surface with an SEM. Therefore, what is happening below the surface is not probable until we can take a cross-section and imagine that way. And in case of transmission electron microscope, we have a very small area as well. We can see the lattice image of that small portion. And the images are always frozen in time image, meaning that once I put the sample or TEM grid inside the TEM, it stays fixed, and I get a single image on that 3 millimeter or so area, from which we can determine the lattice structure. If we are able to make another sample where the damage is, then we can see that damage or the change in lattice structure. But here we are talking about, the whole volume image of a given volume. It can be few micron by few micron by few micron, or few millimeter by few millimeter by few millimeters, or alternatively, the whole wafer. So, and this is a non-destructive and non-contact. So not only the surface, what's happening below the surface, as you can see in the middle image, that becomes very clearly visible. This is the distinction or capability that T-ray, particularly the way we have implemented the T-ray at ARP, offers in contrast with all other technique.
Right. And of course, the obvious to our listeners and viewers today is that once you've prepped that sample for SEM or TEM, you can't get these types of cross sections, or certainly the volumetric imaging, without destroying the sample. In the case of T-ray, which is also non-ionizing, that sample can be put under additional stress and tested again if necessary.
Exactly
Okay,
right.
very good. All right.
Okay.
Mhm.
So if I may move on.
Yes.
Then in the last time we also discussed the volume image and the layers, and as well as how we can do the measurements of either different layer or the whole structure. And then particularly the lattice image, and from which we can measure the lattice parameters, but it also let us inspect the nanograins that forms within even a single crystal lattice. So, and then the interface. When you put materials on top of each other, then the interface plays the most critical role of functionality. And if the interface is good or not, what kind of interface has formed, all of those can be imaged and quantified.
Okay.
So with that, let us move on to the second part of the gallium nitride, in particular the time domain spectroscopy and deep level spectroscopy. And I will explain both of them. The basic, very fundamental principle of spectroscopy is that when light interacts with certain matter or any matter, there are so many physical processes can happen. Namely the green blurbs, reflection, refraction, scattering, interference, absorption, diffraction, and transmission. These are the main ones, and each of them has different kind of phenomenon that can, like reflection can be specular, diffuse. In fact, all reflections are diffuse reflection that will come later. Then, of course, the refraction is refraction. There are different kind of, small angle refraction as well. Then there's, in scattering, you can have Raman, Rayleigh, or Mie effect. Then in absorption, you have electronic, vibrational, rotational, In fact, in absorption, there can be also translational and conformational resonances that can happen. And of course, diffraction and transmission. So, in summary, these 7 main different wavelength or any energy, including terahertz, interact with matter, and then the total intensity as incident on that matter becomes part of the 7 different effects if they are all there. A lot of times all of them are not present in a single material or a given material. Primarily there is reflection, absorption, and transmission. So those 3 intensities IR, as you can see here, the incident intensity I sub 0 is sum of 3 different way that light will interact. In our case, of course, you have to consider the T-ray in case of light. So when we incident terahertz radiation or T-ray, we will also consider those 4 main effects. One is the reflection, another one is the transmission, and the scattering and absorption. So all 4 may or may not be contributing equally to the information that we need to extract. But if we can measure the, let's say, reflected beam compared to the incident beam, that gives us a lot of information. And then the same thing happens for transmitted ray, because the transmitted ray will also have information about the scattering and absorption. Because of the sum total of them should be equal to the incident energy.
Okay.
Many of these informations are available from other techniques such as Raman spectroscopy. However, they also have limitations, pretty significant limitations, which is overcome by T-ray. Particularly, T-ray is sensitive to all kind of resonance in a molecule. As you said in a previous slide, that there are not only translational, vibrational, rotational, and torsional. All these kind of resonance are there that T-ray can be sensitive to, as opposed to infrared or Raman, where sensitivity comes from bond vibration. So the jargon is that infrared shakes the bond, but T-ray shakes the whole molecule. So we get a lot more information, which has pluses and minuses, as we'll show you very soon. But sensitivity is a key issue. Why? Because as you can see here, a simple water molecule, when they have the diatomic molecule as a function of displacement during a vibration, then that is expected to generate so many absorbance peaks on the right side over that, given the wavelength range, some 1200 to 2000, vibration rotation spectrum alone of the HOH bending mode of water vapor is expected to demonstrate that many absorbance peaks, as you can see in the graph here. So this is from the textbook case of book published by Griffiths and DeHassett in 2007, published by Wiley. However, if you take the water or water vapor and put it in an FTIR machine, you get only 1 peak. So why is that? That is simply because the sensitivity of the machine is not there to sense all the absorbance that's happening. And so that's a critical issue. So in our case, we have this experimental setup where we have a sample in front of our spectrometer, terahertz time domain spectrometer. And then you can see the 2 ways to get the spectrum one in the transmission mode, the other one in the reflection mode. However, even there are cases of translift reflectance measurement, which is sometimes important. So all three of the modes can be deployed, or one or the other can be deployed. And samples can be either solid, can be liquid, can be gaseous as well.
Right.
Particular.
I was going to say the example of the sample that's mounted, that could very well be a cuvette holding a liquid sample, a colloidal sample.
Absolutely.
It could be a small chamber or a large chamber holding a gas.
Yes, we have
gases.
another cases, their chamber that has a gas inlet and gas outlet. So
yeah. And T-ray is not really affected either the imaging or the time domain spectroscopy. Say if the a chamber was under a high vacuum and at an elevated temperature.
Absolutely, T-ray will be sensitive to all of them. If you, I mean, if you, let's say, if you
would just need to calibrate for that.
Absolutely, absolutely. You will and need to calibrate for that. But given a chamber, and if your gas pressure is changing, and then T-ray will sense that as well.
Okay.
Or if the temperature is changing, that will be sensed as well. So this is as I said, this is the most sensitive portion of the electromagnetic spectrum, and we certainly be able to make use of this sensitivity in different ways. So for the completeness sake, the technique that is applied here is called the pump probe technique for spectral measurement. So as you can see, this is a schematic diagram of the spectrometer circuit. So it's basically the pump probe technique as was proposed by Professor Sewell, who won the Nobel Prize in chemistry in 1999 for this kind of femtochemistry techniques. So he is credited for this pump probe technique where, think about in the terahertz region, there is no electronics that can measure the frequency. None whatsoever. In fiber optic, where I have some background, we use eye diagram in gigahertz range, high megahertz to gigahertz range. Just technical eye diagram with the oscilloscope. That gives us a way to sense that. However, when you go into the terahertz range or high terahertz range, frequency measurement is not possible by electronics technique. So Sewell came up with this pump probe technique. Thomas Sewell from University of Washington, originally an Egyptian born in Egypt, but American citizen. So he came up with this very smart technique. What happens here, as you can see in the diagram, that this source beam is split into two arms. One of the arm is a pump beam, the other one is called probe beam. The pump beam goes through an optical delay line, and this optical delay line creates the femtosecond time axis. Then this from the optical delay line, it goes to a terahertz emitter, where terahertz is generated. And we particularly found a way of coupling that terahertz to a multimode fiber optic cable, via which it is delivered to this circuit here, terahertz circuit here, and the sample is placed somewhere here. And then we also have a detector on the transmitted side and also detector on the reflected side. And so it's a pretty complicated circuit, but I'm trying to show here as simply as I can to explain the concept. So the basic concept is when the terahertz beam is interacted with the probe beam, then the interferogram happens in the time domain. So we record this time domain interferogram over a few picoseconds. And so this is also, that's why it's also called an ultra-fast technique for probing material, because if the resonance is happening in femtosecond region, which is very, very fast, then we need fast process to track them down. And this is the another rationale of time domain spectroscopy. So basically, this time domain interferogram is recorded, and then Joseph Fourier, one of the smartest mathematician in the history, his technique is utilized to convert the time domain signal into frequency domain signal. I don't know if you have any question at this point. Otherwise, I'll move on.
Not at this point, Dr. Raman. Thank you. Please proceed.
Okay, thank you. So these are the examples I have gotten from. I wanted to show that how the time domain signal is converted into frequency domain signal. So this is a work I found from Physical Review of 2021. I forgot the author's name here. But anyway, so basically this is the time domain signal. And if you take the Fourier transform, you get the frequency domain signal. And so the y-axis is dB or loss, which is the absorbance. So, so we are now tracking the absorption by different resonances in a molecule by terahertz time domain spectroscopy. And then when we talk about the Fourier transform is not a single entity, single thing. The mathematics allows us to do different kind of transform as needed and as has been established by various groups of scientists over the many, many decades of this technique. So in our software, we have built in all of these capabilities. So simple Fourier transform, Fourier spectrum with data window, and I will explain that. And then Fourier spectra with data window comparison. You can compare two different filters. And then Fourier spectra of segmented data, Fourier multi-taper spectra, Fourier spectrum of unevenly sampled data. This is very important because most of the experimental data is not evenly sampled. When we are acquiring data over, as you can see here, picosecond from -5, 1.5 to 1.5, so that's 3 picosecond. Over the 3 picosecond, all the data points that are here, they can never be equidistant because of the experimental situations. And NASA dealt with this problem a while ago because most of their extraterrestrial data, as they collected, were never equidistant, cannot be. So they came up with this Fourier spectrum of unevenly sampled data. And then we have learned from them, taken pages from their book included in our software. Then there is also autoregressive spectrum. There are also autoregressive spectrum with order exploration, autoregressive spectrum with algorithm comparison, moving average spectrum. ARMA is a famous technique that is autoregressive moving average spectrum. Pronin spectrum is another useful thing I will explain. A minimum variance spectrum, eigenanalysis spectrum, also very important thing. And short-time Fourier transform is quite different than regular Fourier transform. It's a short-time Fourier transform is a three-dimensional approach. And why three-dimensional? Because when you do the time domain frequency, time domain transform into the frequency domain, you're losing time and you're getting frequency, which is very important, but why I cannot keep the time as well. So that's where this short time Fourier transform comes, that it keeps both the time and the frequency in the transformed picture. as well as this wavelet transform is another very important transform. Is also keeps both time and the frequency. And the wavelet transform has several different variations. So as you can see, the tools, the analysis tools are not a one-trick pony. So you have to have all of these collection for an analytical scientist to be able to do the correct analysis of the system that they're given.
Of course, this is all built into the Terra spectra.
Absolutely.
Yeah.
These are all supplied with the Terra spectra.
Very good. Thank you.
So now, when you build a spectrometer, there is a obligation of validation, calibration and validation. So what we have done is we have compared with available spectrum, available work in the literature. And this one is the water spectrum. So as you can see in the low frequency region, it matched very well with some discrepancy. And this discrepancy comes from the fact that when this paper was published, they used the water vapor for the investigation. However, we used liquid water, liquid DI water. So, there is thing called liquid, the water as a monomer and water as a polymer. So believe it or not, in gaseous phase or in vapor phase, waters can be treated as monomer. However, liquid water, where all the monomers are put together, becomes a water polymer. So in other words, the volume or the bulk water causes the variation in the absorbance peak.
That's extremely insightful.
Yes, and if we didn't see this difference, then we initially we thought, why is there a difference? This should not be, but then there should be. The difference should be there, and that's what we have.
So even something as, quote, simple as a water molecule in a different state will, the T-ray has a sensitivity to pick that up.
Exactly right. And the whole spectrum is way more complicated, so I'm not bringing here.
Okay.
Another example I'm bringing here is polyethylene. The polyethylene is a common background, used as a common background in a lot of FTIR experiments. So if you have a sample in solution, then what we do is we put it on a polyethylene plate and let the solvent dry and take the spectrum. And given that we know the polyethylene spectrum, then we can separate the peaks due to the sample and then interpret them. That's the idea. What is difficult in T-ray is that, as you can see on the this spectrum over in the red, that is the spectrum published in these references. So Sigma Aldrich, Terahertz database, and Fresnel by MIT, they have verified the polyethylene spectrum like this. But when we take polyethylene spectrum with T-ray, good or bad, we do see all the peaks that they have, but we do see more peaks like here that other techniques did not see. So it's a good thing and bad thing. The good thing because we have now the option of interpreting those additional peaks for what they mean. On the other hand, they have not been verified by techniques that are already out there. So it's a challenge.
So let me ask this question. To date, are there any other techniques out there that can get this data and validate it, as far as we know, that are as sensitive as T-ray are?
Right. Not experimentally, but there are other examples, and your question is very important. Other examples, I don't have, I'm not working with that one here, but we have verified the fullerene spectrum. I had another paper where we worked with fullerene samples. Fullerene or buckyball is the big carbon-60 molecule, right? It's a huge molecule.
Right.
So that has a lot of vibrational and rotational and all those kind of peaks, absorbance peaks that have been studied extensively both by experiment and theory. So there are papers that we compared and we showed that that paper goes on showing very details of the all the possible vibrational states or absorbance states and their degeneracies by both experimental and theoretical approach. So in theoretical, they have predicted so many states there can be, but when they did the experimental by IR or NMR, they see only few. So when we have taken the spectrum of the fullerene and compared, we're able to compare with the predicted as well as experimentally found states, and it checks out a lot closely. So I'm not talking about that one here,
Right.
but as you can imagine, when you see more, it gives a challenge. It brings a challenge of interpretation.
Understood. However, and forgive me if I ask this question and we can't talk about it due to confidentiality, but regarding fullerene and indahedral fullerene with the T-ray detection of certain molecules, can that other techniques simply in the world could not detect, and you did some blind studies on that. Are you allowed to talk about that?
Yeah, absolutely.
Just briefly here. What
Yeah,
did you
because
do?
we have already published it, and my advisor who were so kind to provide those samples, he left us, which is a big loss for the scientific community. But I'll be happy to talk on the fullerene in another podcast.
Okay. So, but I just want to point out that Teraspectra T-ray time domain spectroscopy was able to detect molecules with as indahedral to fullerene that no other method known was able to detect.
Well, to detect the way T-ray could, yes, absolutely.
Okay, all right, very
Particularly
good.
the endohedral portion of it, as you can see, the endohedral, meaning that the fullerene molecule is a huge molecule. It's a big soccer ball-like molecule. So the scientists from USA and Japan collaborated, and they found a way to open the cage, as they call it, is a cage, C60 cage. So they found a way to open the top portion of that cage, took the carbon away, and then introduced hydrogen and deuterium molecule in there, and tritium as well, and then they closed it. So this becomes, they call it a rotor in a cage, because those endohedral molecules inside this C60 molecule loses a lot of motion, but still can keep the rotational motion. So this is a nice way of probing, and we'll get into that at another
Okay,
time.
very good. That's a whole other discussion. So
yes.
Thank you so much. Please proceed.
Absolutely. So let's move on. Okay, so basically we claim and we have demonstrated that the spectrometer checks out with the existing knowledge, but it also produces additional peaks that can be interpreted. So with that, now I talk about the deep level spectroscopy. So most of the times we take spectrum from the surface. But the one purpose of T-ray is that it can penetrate deeper. Therefore, we are able to probe not only on the surface, just like in imaging, we can go deeper and see what's happening in the deep at certain depth of a given sample, both by imaging as well as by spectroscopy. Then we can connect this spectral interpretation with the image and gives a lot better picture, lot better interpretation and knowledge about certain system than only one thing.
And that's all coming from the same data set, essentially. I mean, one scan in time. Is that correct?
Yeah. So in case of spectroscopy, it is not imaging. So imaging and spectroscopy are different scan. In case of imaging, you have that the time, the delay line that produces the time axis, and and also then the interference is the key here, because optical delay line causes the pump probe action, from which we get this interference or interferogram peak.
Okay.
In time domain, this is not frequency domain. But in imaging, we don't have to do this. In imaging, we don't deploy the delay line. All we do is, scan the volume and generate the image.
Okay, very good. Thank you.
But because both of them are on the same system and in real coordinates, so you can be exactly where you want to do the investigation. So here, what I'm showing is the gallium nitride film that I showed you before, that we are going across the depth to see. So these are the interferograms. They're the same data, just two different view. The intensity axis is not shown here, but this is the intensity axis, and we're going deep into the sample at every 50 nanometer in this experiment. And then we want to see that how the surface chemistry or whatever has happened in the subsurface, is there anything change inside the thickness of the sample? And the samples are 2 micron thick that we knew. So then once we have the interferogram, this one, I've just taken only one from here. This is the same data. So if I take only one, this is how it looks like on the surface. Now, there are a lot of information right in this one single interferogram.
Sure.
As you can see in the next graph, I have plotted the real part, the imaginary part, and the absorbance. So basically, you have the real N, imaginary part is usually called K. So the total refractive index is N plus IK. I haven't written it down here, but so if I want to get the refractive index, what we call is an effective refractive index. Then all we have to do the N square plus K square and the square root of that. And because it is a function of frequency, therefore we write function of frequency. Because for most measurements, we are not discriminating as a function of frequency. We take one point, but frequency dependence is important, particularly when you want to make a communication device and that kind of thing with gallium nitride. Then you need to know its frequency dependent behavior. And that is important in our measurement, that we're not just making one spot measurement, we're making a spectrum from which we are now able to do the effective refractive index calculation over the entire frequency range of 30 terahertz that we have. So basically,
I think that's a very, and again, we won't go into depth, but this technique has quite a lot of applications in communications, telecommunications, in such a way that a lot of manufacturers, I don't think, have even looked at these materials and the possibility of discovery of other materials that could be utilized in telecommunications. I mean,
Yeah.
GaN being just one material. You mentioned the frequency aspect of this that can be evaluated, and uh, so anyhow, that may be another discussion for another time.
No, that's very important point. And one thing I think I should note here that you see here is I have shrunk the x-axis to 10 terahertz, and I have then zoomed to only up to 1 terahertz just to show that these busy lines over here, how do they vary?
Right.
The red one is the real part, the
Yeah.
blue one is the imaginary part. They are 90-degree out of phase, as you can see. And and what it looks like a straight line over here is actually there are a lot of features in there.
Sure.
So then from these two, we have calculated the absorbance, and here we have calculated the refractive index. Both the spectrum look pretty much the same except for their value. So the frequency dependence of the physical parameters are very similar because it's the same sample. If you have gallium nitride and it is gallium nitride, therefore the frequency dependence of absorbance or effective index or magnitude, whatever we are interested in, they have pretty much the same spectrum over this frequency range as we are dealing with, which is about 30 terahertz, 30 some terahertz. So here is the depth dependence, the interferogram that I have here. From this interferogram, now I have analyzed 5 of them here as a function of different depth. These are all 5 separate, and these are all 5 on top of each other in the same plot. So on the surface, half micron, 1 micron, 1.5 micron, and 2 micron. This is all 5 spectrum are here. As you can see, these peaks at the very lower, the red one comes from the moisture, ambient moisture, but the other small peaks, they all fall each on top of each other up until here. Beyond this point, the spectrum at very high frequency gets separated as a function of depth. But up until about 5 or so terahertz, they fall on top of each other. So this is important because the depth dependence has to do with the channel characteristic that we'll come to the HEMT one next in the next podcast, and we'll do the frequency comparison of the channel characteristic at there. But this is, just to show you that this is important, and we are able to track that down with our depth-dependent spectroscopy.
Sure. And what's interesting here, you pointed out that the surface GaN analysis having a slightly different, it's showing moisture. And obviously, that's very important. Going beyond just moisture for different environments, GaN is being used a lot in space applications now.
Yes.
And the capability here to analyze do a deep spectroscopic analysis under vacuum and temperature, all kinds of different conditions for space applications. I don't know if there's another technique that can really show this level of deep analysis. That was just a comment more than a question. So please go ahead and
no, it's important comment because additionally in this space you have space environment is not only lack of temperature cold, but also have a lot of extraterrestrial radiation.
And not to mention on the other side of the spectrum is automotive, which is a completely different type
Yeah,
of environment that is one of the most hostile
hostile.
here on Earth, anyway.
Yeah.
So,
So in our HEMT presentation, we'll have a little bit about radiation effect. But there are, as you said, there are a lot of things that can be done with this instrument. I mean, this once you have this instrument,
it's all about deep scientific discovery. I mean,
yeah,
because
yeah,
and of course, you in your lab, you can't cover every possible uh, experiment, uh, and this is up to the scientists and the industry leaders who want to discover not only new materials but how they interact with the environment.
yes,
So the Terraspectra can do in situ analysis, kinetics. So go ahead, Dr. Raman. You
yeah.
can
It's getting
please
the full
proceed.
picture of a material. A material in my one of my advisors from my PhD work said, if you characterize something and you don't characterize everything about it, you're going to have to do it later anyway. So
Right, right.
now or do it later.
And basically, this allows you, TerraSpectra allows you to do it more or less all at one time. But
Yeah,
that,
yeah,
yeah, okay,
that's right.
very,
That's
very
exactly right.
good.
Right. So then what we learned from, so I have reproduced the spectra in terms of wave number here. So what we learned from here is so doing a literature search, I found these are the peaks that they have reported for GaN, for gallium nitride. But then if you look at this spectrum, you see the peaks are a lot more of them than that has been reported.
Right. And
So
that's simply because other methods don't have the sensitivity.
don't have the sensitivity.
Okay.
And this is a good thing and and a bad thing.
Right.
Bad
Well,
thing
for
is
discovery, you need to have all available information.
absolutely, and which is what it gives. But then if I'm a lazy researcher, I would say, oh my God, I cannot explain all of these things.
Well,
So
you could do a
why bother?
thesis on one peak,
Yeah, yeah.
right?
All they want is one or two peaks so that they can assign certain chemistry to it and get done. But they are, by the nature of the molecule, there are so many things as the even the textbook is showing. So we
Yeah.
need we need tools to discover all of them, and which is what we have here. And then that is the last slide for spectroscopy. But the spectroscopy, will, of course, will come up in this one, the HEMT, high electron mobility transistor based on GaN, which is the subject of next podcast.
Excellent. Well, Dr. Raman, uh, quite frankly, that was an amazing introduction, and so I greatly appreciate it. So much more to talk about, and of course, we'll have further podcasts. We'll continue with GaN, and on the next one. Just one material of countless materials. Um, so, what would you say to people just in the semiconductor industry, and then the users, say for space applications, telecommunications, um, automotive, all of these industry areas? We didn't even touch on biomedical and biomaterials. And of course, this is all about nanometrology as well. But what would you say to industry leaders in the semiconductor world, for instance, that are simply trying to make a better device? It's important to lower cost, to know how these devices are going to work out in the field, what their failure rates may be, not to mention just simply improving the process of manufacturing integrated circuits and memory and CPUs and graphical processors. Artificial intelligence is impacted. So that's a big question, but simply what would you say to industry leaders that are spending millions and billions on all kinds of tools, and the TerraSpectra has the capability to do what an AFM, an SEM, a TEM, X-ray, XRD, E-beam, optical, infrared, and for a competitive price and a collaborative effort, what would you tell these industry leaders?
There's a lot to run. Industry is doing very well, but they also have a lot of critical problems. For example, remember in the first podcast, we mentioned that it's so difficult to grow gallium nitride bull. Difficulty is because it has to be processed at high temperature. There are a lot of competing techniques, but none of them has gained the maturity like silicon has, or even silicon carbide has. So GaN is still an epitaxial process for a lot of applications, but developing the ability to form a big ingot and get a lot of wafers out of that is critical for gallium nitride to become a viable industry.
And
so
that could also apply to silicon carbide at this point.
Also, it does, yeah, but it does. Even in silicon, there are still a lot of things. Silicon is the most matured technology of all the semiconductors, and even yet, silicon has issues that we can come at another time. So this tool is meant to alleviate the issues that the industry is facing. How? Because seeing helps us to focus where we need to fix the problem. Until we know where the problem is, we cannot do nothing about fixing it.
Right.
So that's the whole point, that electric stress. Gallium nitride is supposed to take high voltage and function well. And yet we have seen in the previous podcast that the lattice damage happened under high electric field stress. So now with that information, with that process, what was that process? Was it CVD or something? Then what can we do about fixing that? Sure. So lattice is capable because it's, it has a wide band gap. Therefore, it should be capable of taking electric stress, and yet sometimes it did not. So how do we fix that? This information is critical to go about making a better gallium.
Sure. Well, I will go out on a limb here and say, just in terms of putting a gallium nitride power device under high energy, that TerraSpectra, and you can correct me if I'm wrong, but TerraSpectra has or potentially has the ability to, in real time, watch what's going on under high energy conditions.
Yeah. In real time, so you have to, it's a complex problem, always need to be split into simpler parts as possible, as simple as possible. So exactly because the imaging or even spectroscopy is a two-step process. First, we take the spectrum, the time domain spectrum, then we convert it into frequency domain spectrum to see where the peaks are, et cetera, et cetera. In imaging, we first scan a volume, then convert it to the image, and then we connect the spectrum to the actual material to see or infer what is happening. But what is important in industrial applications is that even simple reflection measurement or simple transmission measurement tells us a lot. So lattice dilation, lattice damage causes lattice dilation. Lattice dilation changes the property of the material, density, refractive index, everything gets changed. So if we track only one thing, let's say just simple transmission or simple reflection, that tells us a lot because of the stability of the instrument. If nothing happens, the reflected intensity will stay as a line, or so is transmitted intensity. If something happens, it will show in the both transmitted and in reflected intensity. Mm-hmm. It's similar, very similar to, remember, the kinetics, the chemical kinetics that we have tracked in one of the applications. So the very same thing can be done for semiconductor lattice as well.
Sure. Well, Dr. Raman, I just want to close out by pointing out to our viewers that this tool is not only for research and development, but it can also be used very clearly as a straight up metrology type tool in semiconductor and other industries. But if you want to utilize the tool for deep level scientific discovery and research and development, it can be done. If you want to do something as straightforward as determine what die on a whole completed wafer are good versus failed, that die that'll fail, this tool can be applied in that way as well.
With the slight different configuration, the tool is capable of getting into in so many areas. The one we have in our laboratory, we make it in a versatile for a versatile application, but can be tailored to one or two specific applications.
And finally, there is really no practical limitation. Well, there are practical limitations on sample size, but a sample size, the size of the sample doesn't matter.
No, size, shape does not matter. We had geological samples like rocks in different shapes that was investigated by someone who was interested in transformation of some kind of liquid in those rocks. So the tool is versatile. Which one we use depends on sample configuration as well as on the measurement that we do. But the tools are available here.
Very good. Well, Dr. Raman, this has been very informative and it's been a pleasure. We will reconvene shortly for another podcast to discuss more about the TerraSpectra T-Ray and Applied Research in Photonics, Inc., ARP. So you have a wonderful day. Look forward to speaking with you again.
Thank you, John. Thank you so very much, and talk to you soon again.
Thank you. Bye.